And what is differential equation? Today we discuss about the differential equation. What is the differential equation? A differential equation is a mathematical equation that relates some function with its derivative. In application, the functions usually represent physical quantities, and the derivative represent their rates of change, and the equations defines a relationship between the two. Because such relationships are extremely common, the differential equation plays a prominent role in many disciplines, including engineering, physics, economics, and biology. In pure mathematics, differential equations are studied from several different perspectives, mostly concerned with their solution, which is the set of functions that satisfy the equation. Only the simplest differential equations are solvable by explicit formulas. However, some properties of solution of a given differential equation may be determined without finding their exact form. In a self-contained formula for the solution is not available. The solution may be numerical approximate using computers. The theory of dynamic systems put emphasis on quantitative analysis of systems described by differential equation, where many numerical methods has been developed to determine solution with a given degree of accuracy. And here is some example. For example, in classical mechanics, the motion of a body is described by its position and velocity as the time value varies. Newton's law allows this variable to be expressed dynamically, which given the position, velocity, acceleration, and various force acting on the body, as the differential equation for the unknown position of the body as a function of time. In some cases, this differential equation, which called an equation of motion, may be solved explicitly. Differential equation also can be divided into several types, which is ordinary differential equations, partial differential equations, nonlinear differential equation, and equation order.
What are the properties or characteristics of ordinary differential equation ODE? An ordinary differential equation ODE is a differential equation that involves only one independent variable. There are some examples. dy over dx plus 5y equal to exponent x, or d2y over dx squared minus dy over dx plus 13y equals to 0, or dx over dt plus dy over dt equals to 2x plus y.
So today we discuss about the solution for solving the differential equation. A differential equation or differentiation equation contain derivatives and differential. Our task is to solve the differential equations. This will involve integration at some point, and we mostly end up with an expression along the lines of y equal to blah 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 blah. Recall from the differential section in the integration chapter that a differential can be thought of as a derivative where dy dx is actually not written in fraction form. Example of differentials: ds, this means an infinitely small change in s. d theta, this means an infinitely small change in theta. dt, this means an infinitely small change in t. Example of differential equation. This is example 1. We saw the following example in the introduction to this chapter. It involves the derivative dy dx. dy dx equal to x squared minus 3. As we did before, we will integrate it. This will be a general solution. So we proceed as following. Y equal to integrate x squared minus 3 dx. And this gives y equal to x cubed divided by 3 minus 3s plus k. K is the constant. But where did that dy go from the dy dx? Where did it seem to disappear? So now let us see. In this chapter, we appear to be integrating the s part only on the right, but in fact we have integrated with respect to y as well on the left. DEs are like that. You need to integrate this respect to two or something small different variable one of a time. We could have written our task only using differentials. Sorry for that. dy equal to x squared minus 3 ds. as I did was to multiply both sides of the original dy ds in the question by ds. Now we integrate both sides. The left side with respect to y that y we use dy, and the right side with respect to s that y we use ds. Integrate dy equal to integrate s squared minus 3 ds. Then the answer is the same as before, but this time we have arrived at it considering the dy part more carefully. Y equal to s cubed divided by 3 minus 3s plus k. K is the constant. On the left hand side, we have integrate dy equal to integrate 1 plus 1 multiply dy to give us y. Note about the constant, we have integrate both sides, but there's a constant of integration on the right side only. What happened to one of the left? The answer is quite straightforward. We do actually get a constant of both sides, but we combine them into one constant k, which we write on the right hand side. And in example 2, this example also involves differentials. Theta square d theta equal to sine t plus 0.2 dt. We have a function of theta with d theta on the left side and a function of t with dt on the right side. To solve this, we will integrate both sides one at a time as follows. Integrate theta square d theta equal to integrate sine t plus 0.2 dt. Theta cubed divided by 3 equal to negative cos t plus 0.2 plus k, which is the constant. We have integrate with respect to theta on the left and with respect to t on the right. Here is the graph of our solution, taking k equal to 2, constant equal to 2. Then this is the graph. You see yourself lah. Solving a differential equations. From the above example, we can see that solving a DE means finding an equation with no derivative that satisfies the given DE. Solving a differential equation always involves one or more integration steps. It is important to be able to identify the type of DE we are dealing with before we attempt to solve it. Okay, thank you.
Next is explain all the methods to solve ODE. There are 3 methods to solve ODE. There are integrating factor, substitution, and Bernoulli differential equation. Integrating factor. If we have a linear differential equation in the form of dy over dt plus function p times y equal to function g, then we can let mu t equals to exponent integrate function p dt as our integrating factor. After that, we multiply both sides of our differentiate by integrating factor to solve differential equation. Example, solve dy over dt plus 2y over t equals to sine t over t squared by using integrating factor. First, we need to let our integrating factor mu t equals to exponent integrate 2y over t dt equals to 2t squared. Then, we're using our integrating factor t squared to multiply both sides of our equation. We will get t squared times dy over dt plus 2ty equals to sine t. Then, we differentiate t squared y equal to sine t. After differentiate, we integrate d over t squared over y dt equals to integrate sine t dt. After the integration, we will get y equals to negative cos t over t squared plus c over t squared, where c is an constant. Substitution. By using the substitution v equals to y over x to solve the first order differential equation. Example, solve y prime equals to x squared plus y squared over xy by using substitution. First, we will write this differential equation in the form of y equals to f bracket y over x and simplify it. We will get y prime equals to bracket y over x power negative 1 plus y over x. Then we let v equals to y over x. Then we will get y equals to vx, and our y prime equals to v plus x times v prime. And thus, we can use this substitution in our differential equation above to get that x times v prime equals to v power negative 1. Then we move our v power negative 1 to the left hand side and our x move to the right hand side. We will get v times v prime equals to 1 over x. After that, we integrate both sides. We will get v squared over 2 equals to ln x plus c, where c is a constant. V squared equals to 2 ln x plus 2c. V equals to plus minus square root 2 ln x plus 2c. Lastly, our y is equal to plus minus x square root 2 ln x plus 2c. The third method is Bernoulli differential equation. A nonlinear first order differential equation in a Bernoulli differential equation, if it is in the form y prime plus function p x times y equals to g x y power n, we can solve this class of differential equation by using the substitution v equals to y power 1 minus n. If we differentiate v, we get that v prime equals to 1 minus n times y power negative n times y prime. We then divide our original differential equation by y power n and apply this substitution to get a linear first order differential equation that can be solved using some of the other method. Example of Bernoulli differential equation. Solve y prime plus 2xy equals to 3xy cubed. First, we dividing the differential equation above by y cubed to get y power negative 3 times y prime plus 2x y power negative 2 equals to 3x. Now, we will make the substitution v equals to y square, and so v prime equals to negative 2y power negative 3 times y prime. Applying this substitution, and we will get v prime minus 4xv equal to 6x. We can solve the integral on the right by using substitution. Let mu t equals to exponent integrate negative 4x dx. Then we will get exponent negative 2x squared. Multiplying both sides of the differential equation above by the integrating factor, and we will get exponent negative 2x squared times v equals to integrate negative 6x exponent negative 2x squared dx. Next, we can solve the integral on the right by using substitution. Let u equals to negative 2x squared. Then du equals to negative 4x, and so 3 over 2 du equals to negative 6x dx. Hence, we will get v equals to 3 over 2 plus c over e exponent negative 2x squared, where c is a constant. We will now use the substitution v equals to y power negative 2. Then we will get y squared equals to 1 over 3 over 2 plus c over exponent negative 2x squared.